Saxon's Calculus Lesson 98 is about separable differential equations. Now, the beginning of this lesson is a lot of terminology. Although some of it is new, I feel like a lot of it is just basic review. And so they are reminding you on page 478 that when we add the plus c at the end of an integration, we have made it a general solution because that c is a constant that could be changing it. However, if instead of saying 4x plus c, I would say 4x plus 15 equals the y, then I am being specific and I'm giving a particular solution. The other thing they used for general solution is a family of solutions or a grouping of solutions. I also skipped their separable differential equation, meaning that you can separate the individual parts to integrate as we've been doing all along. And then they go into reminding you that we have some, what did they call them? No, that's the general and the particular solution again. That we somewhere we have the formulas basically memorized, like e to the kt, like we know how to handle that. And so they're trying to, the terminology was not what was important, I didn't think. They were trying to remind you about this formula that you used a long time ago with bacterial growth or decay, where it was your amount after time has gone by came from your original amount multiplying with e and a set constant for that problem and whatever the time of that problem was. And then on the top of 479, they show you three different equations. They're all the same. It's just when they used V, they were talking about solving for volume. When they used P, they were talking about solving for population. And when they used the S for the equal, they were talking about the rate at which the radioactive substance decayed. All right, and then they jump into example 1, which is a review of a trig manipulation, has nothing to do with the calculus that we've been doing. So, example 1, the rate at which a certain bacteria colony is growing at a given time is proportional to the number of bacteria present at that time. So we know this is our basic formula. When the time is 0, we have 1,000 bacteria. So our original amount is 1,000. Multiplying with e, we don't know the constant. And then when the time is 1, so now I'm going to change that time to 1, we have 10,050 bacteria. Write an equation which describes the number of bacteria present as a function of time. So basically, figure out what the constant is. So if you remember from last year, you're going to do 1,050 divided by 1,000, and that gives you some sort of decimal. To remove the e, you natural log that decimal, and then that leaves you with your 1k, so just k. So whatever the decimal is from natural logging that, and I'm looking here, it is 0.049. Then we are ready to write the equation. So our original amount was 1,000. E with the 0.049 times the t gives me basically a sub t. They used a capital N sub t, doesn't really matter. That's your equation. And then it says, use your formula to find how the size of the bacteria colony when the t is 4. So 1,000 with e 0.049 times 4, calculator that, 0.049 times 4, then take your e to that power and multiply that by 1,000, and you should end up with 1,217, word problem, bacteria, or something along that line to answer that question. Now, example 2. The slope of a curve everywhere is twice the value of the x coordinate. Find the equation of the curve if the curve passes through the point 1, 2. Now, since it's talking about slope, we know that we're dealing with something that has been derived. So when it said that our derivative was twice, so that's 2 times the x. And then we need to work it backwards to integrate it to determine what the equation should be. So that's going to be 1 plus 1 is 2. That divides out and goes away. So it's basically leaving me x squared. Just a second. Yes, x squared. Okay, it just took me a second to find it. And then we automatically do the plus c when we're dealing with the integration. Now, it said to use 1, 2. So we're going to use that to be specific and find what c should be. So our 1 goes in here, so that's going to be 1 plus c equals 2. So c equals 1. Great. Now our actual equation would be y equals x squared plus 1. Example 3. Find the general solution, meaning it has to equal 0. No. Should, but their answer is not going to. Oh, general could be different depending on what the shape is. Never mind. To the differential equation of, so they're giving us x dx plus y dy equals 0. So if we integrate that individually, then this goes to x squared. This one goes to y squared. And we would have the plus c, but since I know that that is now a circle, it should be like x squared plus y squared equals the radius squared. So our constant's going to basically move and say that it equals c. And I realize that technically it should say c squared, but it doesn't really matter because c is that constant. It just wants the overall equation. Example 4. Find the general solution to the differential function. So f prime of x is 4x squared y squared. Then find the particular solution to find the particular solution if the point 1, -1 lies on the graph of the curve. Okay, so we first need to be doing our integration. But before I start the integration, I need to do a little bit of manipulation to this problem. So I know that this implies the dy over dx. And this puts that fraction in here, which throws my problem off. So I need to multiply the dx to this side, and then I need to separate this y back over here to join its dy. So when I divide it away from the rest of the things, that makes it 1 over y squared. So I'm going to write that as 1 over -2, the same thing, because that means 1 over y squared. dy equals my 4x squared dx. Okay, so now we are in a place where we can undo. So when I do that here, that goes to -1. Dividing by -1 makes the whole thing negative. And y to the -1 would then separate it to as a fraction to be back over as y equals, and then 4 stays, adds to 3, divide by that 3, x cubed. And then we would have our plus c from integrating. Now, I need it as, okay, this is not like a set circle or something else, so I need to set it equal to y. All right, so solving that, to solve for the y, I would multiply the y to this side, and I would write this except I'm running out of space, so just follow with me. The y multiplying over here would separate the y, then I would have to divide all of this away over here to the -1, and so that basically is -1 over top of this stuff, which means fraction over fraction, I'm going to flip it. So y equals, and this is going to negate the flipping of this. So the 3 was the only thing in the denominator, and then the numerator was 4x cubed plus c, which is now landing in the denominator. And that's the equation, and then they want me to test 1, -1 I'm looking to see, did they actually tweak that some more for some odd reason? They decided to change everybody's sign. Should not matter. Okay, so now, where is there one? All right, I decided I was really out of space, and so I flipped the page and rewrote the last equation. So we're plugging in that 1 and -1, and that will give us -1 equals -3 over 4 plus c, because we're plugging in 1 for the x. Yes, okay. Then that gives us -4 minus c, and when I multiply it over here with the -1 equals -3. So -c equals, add the 4, 1, then that's going to make it c equals -1. Then I would be able to say y equals -3 over the 4x cubed minus 1. Now, did they change all of those signs? They did. They chose to change all of the signs for whatever reason, but that's acceptable. Okay, so then I know that that lies on the curve. Find the general solution, check, then find the particular solution if the point lies on the graph. Okay, so that, I needed that point just to get to this equation. Now, to figure out what that is, I need to derive. But I'm deriving the original equation, which again was dy over dx equaled the 4x squared y squared. But this is my new y, so we're going to substitute in -3 over 4x cubed minus 1 squared. Okay. Now, I feel like I need to put this all together. So that would be 936 x squared over, and this is also squared. It's multiplying by 1, but it still has to be squared. So 16x to the 6th, because that's 4x cubed times 4x cubed, minus 4x cubed, when I put those together, double to -8x cubed, and then plus 1. Oh, maybe they didn't. Maybe they just wrote it with the squared. We get an identity as a result. We have shown that the quotient y equals 3. Oh, no, I haven't. Okay, it's okay that I did, because I need to be... So what I need to show is that if I take this and derive it, I should get to the same answer. So this one would become dy equals, and because this is a quotient, I have to follow low, which is 4x cubed minus 1, derivative of the top as a constant, low d high, minus high, so that's plus 3. Derivative of this one goes to 12x squared, the minus 1 drops off, over top of the 4x cubed minus 1 squared. Okay, that's why they didn't distribute this one out, because that's the same thing here as the squared. It's okay, we'll see it as we do it. So then, still putting this, I feel like I have a problem in here. The only problem I have is that when I derived that in my head, I said 1, it's 0. 0 times anything means that is knocked off. So that does equal 36x squared over top of, and again, if I distributed it out, it would be that same thing. Since that's the way I wrote it above, I'll write it that way here. And so since the derivative of this answer matched what we had originally with the substitution in here, since they are lining up, then we know that we have the quotient is a solution. Yep, so we've answered their question. Nothing really I can box there. Maybe I would just kind of check mark that. All right, example 5. Use the method of separation of variables to find a general solution for the differentiable equation y prime equals ky, where y is a function of x and y is positive. So if we substitute that then again as dy over dx, and we would put then the dx over here. Now we have dy equals all of that. We can integrate, just a second, I feel like maybe I should be solving for the y. I don't like y with the dx. K could be implying something in the x family. So I am going to move this y over here and make that, it's dividing, so that's 1 over y with the dy. Okay, so if that's 1 over y with the dy, when I integrate, that's going to go to natural log of y, and it should imply the absolute value of, because it said everything coming out with it was positive, comes from, and so that left me with the k dx, which means there's an x going, it was x to the 0 implied, so now it's k with an x to the first, dividing by 1 doesn't change anything, and of course our plus c. All right, so don't need the absolute value sign because it's already positive, but that's okay. And then I need to solve for y. So I need to remove that natural log from the y, which means I need to do e to those powers to fix that. So that would give me y equals e, and now it's getting what we had here before, kx plus c. And e to the c is considered a constant, so we're getting y equals a constant with the e to the kx still there in that format. And then they're saying, okay, if we just do a substitution, we manipulate the problem. What exactly? Use the method of separation of variables to find the general solution. Okay, so a general solution needs to be in the dy over dx, or as they put it, d over dx. Sorry, I'm saying it and writing it the wrong way. So my constant is going to go to an a for an amount with the e to the kx. And that means, and since it came from originally k times y, then it equals the ky, and there is the equation that they're looking for.